The alkali earth metals, which include beryllium, magnesium, calcium, strontium, barium, and radium, are found in group 2 of the periodic table. They all have 2 valence electrons. The alkali earth metals are not found as pure elements in nature, only in compounds. These elements, with the exception of beryllium, are known as alkaline earth metals. These are so called because their oxides and hydroxides are alkaline in nature, and these metal oxides are found in the Earth's crust. The most abundant elements in group 2 are calcium and magnesium. They are the 5th and 6th most abundant elements in the Earth's crust. The other group 2 metals are significantly rarer in nature. Oxide compounds of group 2 elements are found in the Earth's crust. The alkali earth metals have similar properties because of their related electron configurations. Since they all have 2 valence electrons, they form cations with a charge of +2. Shown here are the electron configurations of 4 alkali earth metals. Notice how they all end as S2, showing those 2 valence electrons. The similarities in the electron configurations are even more apparent when written in noble gas notation. They all end as Ns2, where N is the highest occupied electron energy level. Because of their 2 valence electrons, all the group 2 metals form cations with +2 charges. By losing the 2 outermost electrons, they form cations that are isoelectronic with the nearest noble gas. Let's go on and review the periodic trends as they relate to the alkali earth metals. In general, atomic radius decreases from left to right in a period. In groups moving from left to right, outermost electrons enter into the same electronic shell. Therefore, size does not increase. Moreover, outermost shell is held more tightly by the increasing nuclear charge. Thus, we see that an alkaline earth metal has a smaller atomic radius than the group 1 metal in the same period. As shown in the graphic, atomic radius increases down a column because the electrons enter into new electronic shell and inner shells act as screens for outer electrons. Therefore, outermost shell is held less tightly by the nuclear charge. This pattern holds for the group 2 metals as well. Let's consider the ionic size trends. Cations are smaller than their parent atoms due to increased nuclear charge. As mentioned earlier, the group 2 metals typically form ions with a +2 charge. As shown in the graphic, the group 2 cations that form are significantly smaller than the neutral metal atoms. Recall that ionization energy is the energy required to remove an electron from a neutral, isolated atom. A typical equation representing this change is shown. In general, ionization energy increases from left to right across a period. The outermost electrons are held more tightly as the nuclear charge increases. In accordance with this trend, the alkaline earth metals have higher first ionization energies than the alkaline metals. The second ionization energy is the energy required to remove the second electron. Once the first electron has been removed, as indicated in the equation here, Generally, second ionization energies are higher than first ionization energies. One interesting fact you should know: the second ionization energies for the group 2 metals, that is, alkaline earth metals, are lower than the second ionization energies for the group 1 metals, that is, alkali metals. This is because losing one electron for a group 1 metal gives it a noble gas-like electron configuration, and losing another electron from these cations becomes significantly less favorable. The alkali earth metals have relatively low ionization energies. However, reflecting their high tendency to lose electrons, ionization energies for the group 2 metals decrease down a column. So, we can describe the alkali earth metals as electropositive, and they become more electropositive down the column. Hydration enthalpy is defined as the amount of energy released when 1 mole of an ion is dissolved in a large quantity of water. As ionic size increases, hydration enthalpy decreases. Therefore, we observe a decrease in hydration enthalpy from beryllium through barium. The group 2 metal ions have larger hydration enthalpies than the corresponding group 1 metal ions. Many salts of the group 2 metals are found as extensively hydrated salts. For example, magnesium chloride and calcium chloride both exist as hexahydrates. Neither potassium chloride nor sodium chloride is found as a hydrate. However, let's discuss the physical properties of the group 2 metals. The alkali earth metals are silvery white, lustrous or shiny solids. Although beryllium and magnesium may have a greyish cast to them, they are relatively soft metals, though harder than the alkali metals. Like all metals, they are good conductors of heat and electricity. The group 2 metals have higher boiling points than the group 1 metals due to their smaller atomic radii. Similarly, the group 2 metals have higher melting points than the group 1 metals in the same period, although the trend is not systematic. Flame tests are a simple, qualitative way to test for the presence of metals. By holding a sample of a metal salt in the flame and observing the change in the color. The heat of the flame excites the electrons to a higher energy level, and then the electrons emit light as they return to the ground state. Calcium salts produce a characteristic brick red flame. Strontium salts can be recognized by the crimson flame that results. Strontium salts are used to make fireworks that emit red light. Barium gives an apple green color to the flame. Why don't magnesium and beryllium produce colored flames? The electrons are held tightly by the nuclei in these elements, and so the flames do not excite them to higher energy levels. Magnesium, in fact, will ignite in the flame and react with oxygen, giving off an intense white light. Now we should discuss various chemical properties of the alkaline earth metals. In general, the alkaline earth metals are less reactive than the alkali metals. The group 2 metals form a variety of different types of compounds. Our focus is on the oxides, hydroxides, halides, carbonates, sulfates, and nitrates. We'll discuss each of these in turn. Magnesium and beryllium do not react with water because both the metals form an oxide layer on their surfaces. Calcium, strontium, and barium all react with water at normal temperature to form hydroxides. The reaction of calcium with water is shown here. These hydroxides have low solubility in water and are less basic than the group 1 metal hydroxides. In general, for the group 2 metal hydroxides, as the atomic number of the metal increases, the solubility, thermal stability, and basic character all increase. Beryllium hydroxide, unlike the other group 2 metal hydroxides, is amphoteric. It can act as both an acid and as a base. In the first reaction, beryllium hydroxide acts as a Lewis acid by accepting electron pairs from hydroxide ions. In the second reaction, beryllium hydroxide acts as a base with hydrochloric acid. Why do the group 2 metal hydroxides become more soluble down the group? Recall that metal cations increase in radius down a column. As internuclear distance increases, lattice energy decreases. So, less energy is required to separate the ions. The hydration enthalpy, however, decreases less dramatically. The net result is that the salts are more soluble in water. Beryllium and magnesium do not react with oxygen at normal temperature due to the formation of an oxide film on their surface. When burned in oxygen, the group 2 metals form metal oxides. For example, burning calcium in the presence of oxygen forms calcium oxide. Magnesium and beryllium, when ignited, will react vigorously in air, releasing a bright light. Both the oxide and the nitride will form when reacting in air, as shown here in the reactions for magnesium. Calcium, strontium, and barium also react in air to form oxides and nitrides. Beryllium oxide is essentially covalent in character. It is an amphoteric oxide, meaning it can act both as an acid and as a base. The other group 2 metal oxides are essentially ionic substances, and the basic nature of oxides increases from magnesium to barium. With the exception of beryllium oxide, the group 2 metal oxides are basic anhydrides. This means that they react with water to form metal hydroxides. All the group 2 metals can react with halogens, forming halide compounds. These reactions usually occur at high temperatures. For example, calcium fluoride forms when calcium metal reacts with fluorine gas. A sample of fluorite, a naturally occurring mineral of calcium fluoride, is shown in the photograph. The best synthetic route for preparing beryllium fluoride is to heat ammonium beryllium fluoride until it decomposes, as shown in the equation here. Beryllium chloride can be formed by reacting beryllium oxide with chlorine gas in the presence of carbon. Carbon monoxide is a byproduct of this reaction. The halide salts of the alkaline earth metals are essentially ionic in character, with the exception of the halides of beryllium. The beryllium halides are primarily covalent and thus are soluble in organic solvents. In the solid state, beryllium chloride has a chain structure. However, in the vapor phase, beryllium chloride forms a dimmer. These dimmers dissociate into monomers at very high temperatures. The halides of the group 2 elements are often found as hydrates, but these salts are complexed with fewer water molecules down the column. Thus, magnesium chloride is an octahydrate, whereas barium chloride is found as a dihydrate salt. These salts can be dehydrated upon heating, leaving anhydrous salts. It should be noted that beryllium and magnesium salts will undergo hydrolysis upon heating, though, in general, the fluorides tend to be less soluble than the chlorides because of the higher lattice energies associated with the fluoride salts. All of the group 2 metals, with the exception of beryllium, react with hydrogen to form metal hydrides. The reaction involving the formation of calcium hydride is given here. Beryllium hydride can be produced by reacting beryllium chloride with lithium aluminium hydride. The group 2 metals react with acids in a single replacement reaction, releasing hydrogen gas as a product. As a family, the alkaline earth metals have large negative reduction potentials. This feature reflects the strong tendency of the metals to lose electrons, otherwise known as oxidation. Since oxidation cannot occur without reduction, they can be considered good reducing agents. Beryllium has a lower reduction potential than the other group 2 metals because its cation is smaller and has a larger atomization energy. In liquid ammonia, the group 2 metals dissolve to form solutions with a deep blue-black color. Ammoniate salts of the general formula shown here can be recovered from these solutions. The carbonates of the group 2 metals are insoluble. They can be prepared by reacting soluble carbonate salts, such as group 1 or ammonium carbonates, with soluble salts of the group 2 metals. One such reaction is shown here. A photograph of the mineral calcite, a naturally occurring form of calcium carbonate, is shown here. The group 2 metal carbonates decompose upon heating to form the oxide and carbon dioxide, as shown for calcium carbonate here. The White Cliffs of Dover consist primarily of calcium carbonate. The thermal stability of calcium carbonate increases as the metal cation increases in size. Beryllium carbonate is unstable and must be kept in a carbon dioxide atmosphere. The sulfate salts of the group 2 metals are white solids that are heat stable. Beryllium sulfate and magnesium sulfate are water soluble. But the solubility of this class of compounds decreases down the column. This is because beryllium and magnesium ions have higher hydration enthalpies than the other metals in the group. The group 2 metal nitrates can be prepared by dissolving the carbonates in dilute nitric acid. This class of compounds repeats the pattern of the decreasing tendency to form hydrates down the column. For example, magnesium nitrate is found as a hexahydrate, but barium nitrate is anhydrous. When heated, all the group 2 metal nitrates decompose to form oxides, as shown in the equation for the decomposition of calcium nitrate. The alkali earth metals are used for a variety of purposes. We'll wrap up this module with an overview of the uses of these metals. Beryllium is used in many industries. It is used to prepare several alloys. A copper beryllium alloy is used to manufacture high-strength springs. Metallic beryllium is used for the windows of X-ray tubes. The inhalation of beryllium dust, vapor, or its compounds can cause berylliosis, a serious form of mental poisoning. Magnesium is also used to prepare alloys. A magnesium-aluminium alloy is used in the construction of airplanes. Magnesium metal is used in flash powders and flash bulbs for cameras. Milk of magnesia, a suspension of magnesium hydroxide, is used as an antacid. Magnesium carbonate is used as an ingredient in toothpaste. Calcium is used in the extraction of metals from oxides when they are too difficult to reduce with carbon. Calcium, along with barium, has been used to remove air from vacuum tubes. The radioactive salts of radium are used in the treatment of cancer.